So I think today we'll assemble the PCB board for our ESD gun, and if you want to see me making this PCB, I did show this in last week's video. So I'm going to go ahead and I'm just going to assemble this. I'm going to start off with the power supply arrangement, and what I'll probably do is I'll build each section, and then I'll maybe just show you the circuit and we can have a go at testing it. So I think the first components that I'm going to put in is I need to install power connector, which I've got one of those here. In fact, let's use a different one. I'm going to install this power connector, which I forget what they call these, but it's a terminal block design, and that's what we're going to connect the incoming DC supply to. This is going to get switched by the trigger unit on the ESD gun, and so let's solder that in. Now I'm a little bit worried about assembling this because there's no solder mask on it, and I don't know how I'll get on with soldering it without a mask. As I said before, it's been years since I've made my own circuit board, and unfortunately some of these pads are quite small, so I think I'm going to have a little bit of fun soldering these components in. Now, to maximise my chance of success, I think that every joint I touch I'm going to use a bit of a flux pen. Well, I'm going to use a flux pen on it. Now, I've actually previously cleaned this circuit board, and but having cleaned it, it doesn't really look as clean as I would have liked. I think I might also just turn my soldering iron down a little bit because I don't want to lift any of the pads. We'll have to see how we go with this circuit board material. You never know with circuit board materials. I think this modern FR4 is pretty good in terms of temperature resistance and the pads lifting off. But I've actually drilled some of these holes maybe a little bit oversized for the pad size, so I'm a bit worried that I'm going to take some of them off. Anyway, we'll have to find out. So just looking at the circuit diagram here, I think I'm actually going to do the assembly from left to right. Usually when you're assembling a circuit board, it's a good idea, it's good practice to install all the small components like the resistors and stuff like that, and then the bigger things like large capacitors and heat sinks and power transistors, you'd normally install those afterwards. Reason being is because the big components can stop you getting in with your fingers to actually insert the smaller components into the holes. But I think I'm not going to follow that regime. I'm just going to really start from left to right and just assemble the components in order as we come to. So the first things that we've got to install is, well, here I've got a polyfuse, but unfortunately I haven't got one of them, so I'm sure a linker wire will work just as well. And then we've got a couple of resistors here. One of the resistors is feeding an LED which is on the circuit board, and then we've got another resistor which is the same value, and that's going to be feeding a header connector, because that's going to be feeding another LED that we're going to install on the front panel of the ESD gun. So let's get them in. Well, it looks like I've just hit my first minor assembly problem, and I've just tried to insert this LED, which is our power indicator, but unfortunately I can't get the legs into the holes. They just won't go through. So I've actually drilled them undersize. Now, it's annoying that I found this out just now rather than earlier, because once you've got some components in the board, it makes it very hard to put it down flat and actually drill, open these holes out on the high-speed drill. And if you don't have the board presented beautifully flat, you snap the drill. And in fact, unfortunately, I did actually snap a drill in this manually. I was probably a bit clumsy. So looks like I'm going to have to just nip back out to the garage where I was doing the drilling. I'm just going to have to open out a couple of holes here. So there's an LED that goes down here, and then I think there's another LED which goes over here somewhere. So it looks like I'm going to have to open up both sets of holes before we can get it in. So that's a little bit annoying, isn't it? But of course, these things happen when you're building PCBs from scratch. Well, I thought I might just share a quick tip with you. So the problem will be I won't be able to actually put this piece of circuit board down back on the drill table, because the components I've put on it, they're going to stop it sitting flat, and that will almost certainly be a problem for me. So a lot of you might already know about this, but there's lots of times where you have similar problems in electronics. So what you will find will come to your rescue is a big piece of blue tack, because effectively it'll just provide enough support like that. When we bring the drill down, it'll be able to drill through there and the board won't tip up. We might have to optimise the position of the blue tack, but I found that quite a good way of doing it when I've had this problem in the past, so just passing that on. Whenever I assemble a circuit board, I actually try to break it down into little separate assembly tasks. So the first task really was just to wire up this little LED circuit. So we've got our power connector, We've got an output header which is going to feed an external LED, and we've got a power LED on the board, and we've got a couple of resistors which are droppers. So really very, very simple, but fingers crossed, let's put some power on and see if the LED lights up. So I'm going to take that as a pass, and we can now move on to the next stage. Well, there's no doubt you can see I've gone ahead and I've wired up the power supply section, and that really just consists of this LM317, which is a variable voltage regulator. It has a couple of protection diodes on it, which are just to protect it from being backdriven by these capacitors in the circuit. It's also got an external potentiometer, and I've gone ahead and I've wired that up. So that's going to be the front control on the top of the ESD gun, and that's going to allow us to wind up the output voltage, and that's effectively going to control the actual high voltage output. So this has got to have a control on the front panel, so I've gone ahead and I've put that on a flying lead which just plugs in here. So I'll plug that back in. So I think we're at the point now where we need to give it a quick test. So I've got the power supply hooked up. I've also gone ahead and I've got one of these little tiny bulbs, which is the kind of thing that you have in a CB actually. It's what they use for powering up the little SWR radio frequency displays on them. So that's just a little tiny bulb. Let's put some power on. It's connected up to the power supply, and I think I've got the power supply set to current limit at about 500 milliamps. So hopefully that should give us a little bit of protection. Okay, we've got an LED lit up, so that's a good sign. And hopefully, if I just turn this potentiometer now, fingers crossed, that light should come on. Which it does. So that seems to be doing what it should do. Of course, being an LM317, you can't actually go to 0 volts. That's just one of the little niggles of using these, but I don't think that's going to be a problem. I think the input voltage to my circuit, it's about 13.3 volts, so I'm guessing we're probably going to get to about 11 volts output, well 11.8. Now, having gone ahead and populated the power supply section, I can actually report that it really wasn't very difficult to solder these parts in. I thought it might be a bit tricky without having the solder mask on it, but as long as you're careful and you get a little bit of heat into the board first, you know, on the part where you want the solder to apply, you're just going to heat the track up. The solder will wick quite readily onto the copper, but even though I actually give this a good clean with a Scotch-Brite pad, I actually think that it's still quite dirty. I've tried to get it a bit cleaner and I've been struggling to get it clean. I think perhaps the Scotch-Brite that I was using, perhaps it was just too aggressive and too rough, and it's actually created scratches in the copper, and those scratches are maybe trapping a little bit of dirt. So what I've been having to do just to clean up the copper, I've been using this fiberglass pencil, and before I actually put the component in, I've just been going over the pad where we want to put the component, and it has gone bright. It has actually cleaned it up a bit. So I've got various grades of Scotch-Brite pads, and I think the one that I actually picked up and used was probably a little bit on the rough side, so lesson learned there. Just cleaning the circuit board there with a little bit of IPA. I can't really afford to flood this with acetone and give it a good clean, because now I've put this ident layer on, if the acetone gets onto this side, it's going to end up just dissolving all the ident layer, which I don't want to do at the moment. Okay, so I'm going to install this 100 microfarad electrolytic, and then I've got 100 nanofarad. So let me put that one in. So that is C12, which got to get it the right way around, haven't we? That goes there. And then we've also got the C11. Where does C11? C11 goes next to it. So you can see I've got a bench magnifier here. So what I'm doing after every joint, I'm actually just inspecting the joint to look if I'm bridging across any tracks, because there's no solder mask, so it would be quite easy to bridge across something. But those look okay. So I don't think it's very exciting watching me solder resistors in and capacitors. So we'll get them knocked in, and I'll bring you back when it's time to switch the oscilloscope on. So I'm afraid I got a little bit overexcited, so I've gone ahead and I've installed our 555 timer, which is the flyback oscillator, and I've also gone and installed the MOSFET driver stage as well, because it was only 1, 2, 3, 4, 5 components, so I just went ahead and stuck them in while I was doing it. And I powered the circuit up, and you can maybe see that we've got our little bulb glowing again, but it's not actually glowing very brightly, is it? I've actually got the voltage turned fully up, so from the variable power supply section we've got this turned fully up now, but you can see, hopefully you can see, that it's barely glowing. So at first thought you might think, well, there must be a fault because he's got the voltage turned fully up. It was glowing really brightly before and now it's barely on. Well, no, it's actually working perfectly, because the whole purpose of my little flyback oscillator, it's actually a pulse width modulation stage. So although we're actually supplying the same voltage to this bulb as we were before, what we're actually doing is we're switching it on and off very, very quickly. Now, the approximate timings and the calculations, the frequency for this aren't important. I designed it to work around the 10 kilohertz point. So let's have a look at the oscilloscope and have a look at some of the waveforms now, because that'll give you a better idea of what's going on. And I think I'll bring you into the circuit about the point here where we actually got the output from our flyback oscillator and we're going into our driver stage. But I'm going to take you from the output of the oscillator. Now the frequency output from our flyback oscillator here, it's actually a fixed frequency output, but what I can do is I can change the duty cycle of the output waveform. So I'm hoping you can see at the moment on the oscilloscope display, I've actually got the duty cycle turned down very low, and this bulb is glowing very, very dimly. Now it is actually receiving the full 12 volts, full output from my power supply, but it's only just glowing, and the reason it's only just glowing is because it's only on for a little bit of the time. It's only been switched on very, very briefly. So you can see the pulses on the oscilloscope. We're actually switching the light on. So it's actually going on and off really quickly. You can't see it flickering because it's doing it at 10 or 11 kilohertz, but this bulb is actually going on and off very quickly. But what I can do is I can just adjust the duty cycle, the pulse width modulation. So you can see if I adjust this control, this bulb has got a lot brighter, but I haven't adjusted the voltage to the bulb. All I've done is I've just got the bulb switched on for more of the time. So if I actually just adjust the control the other way, hopefully you can see on the oscilloscope that the duty cycle is falling and the lamp gets dimmer. In the previous video you saw me assembling the high voltage electronics that goes within our ESD gun, and I'm hoping you'll remember that inside this box at the end is actually a high voltage relay, and what we want to do is we either want to be able to switch that high voltage relay on permanently, in which point this will be energized all the time with high voltage, or we want to make the relay pulse on and off. So the next part of the circuit we're going to actually build, it's what I've called this pulse mode generator. So it's got a switch on it here, which is going to be a switch on the front panel. So when we actually close the switch, it goes into this pulse mode. So about every second what it's going to do, it's going to close this high voltage relay and it's going to shoot some high voltage out of the end. But there's another type of testing we want to do where we want to keep this constantly energized. So when we open the switch, it will go into what I call the constant mode. So that's part of the circuit, that's going to generate our pulses, and of course I've got some stuff here just gilding the lily, which I want to have a little bit of a sound, and when the high voltage is turned on, I think it's important to give myself a little bit of warning that everything's energized. So I've got an output transistor here which is just going to pull in a little piezo sounder, and also because the output relay, this high voltage relay, does take a little bit of current, I've also got a driver transistor here. So what I think we'll do next is we'll go ahead and we will assemble probably this pulse mode generator, and we'll see if we can get that working. Well, I know that some of you last time seemed to quite enjoy the little Muzak montage I put together for you. So what I'm going to do is I'm going to go ahead and I'm going to put some of these components in now. I'm going to build this up, and you can watch me build this up and listen to some Muzak. Well, I've gone ahead and I've assembled our pulse mode generator, and I've also fitted some components here which are actually to drive the high voltage relay. So it's just a transistor, and it's also got an LED which is going to indicate when the high voltage relay is actually energized, when it's in the closed position. So we've assembled that, and what I'm going to do is I'm going to just put some power on it now. Now I've already tested it, and I've got to report I've actually made a mistake, and it's kind of a rather non-trivial mistake, I'm afraid. The LED is actually blinking away nicely, and there's no problem with that part of the circuit, and at the moment I've got it set to its kind of well, it's pulse mode, so it's doing what it should at the moment. The problem is when I actually switch the device into its what I call the continuous mode. So in the continuous mode, the high voltage relay should be energized, so the contact should be permanently closed. So I'll just put it into the continuous mode. And the problem is, as you see, the LED has stopped blinking, and the reason it stopped blinking is because the output driver stage isn't being enabled, it isn't being turned on. So this is my pulse mode generator circuit, which is, again, it's very much the same circuit as actually the flyback oscillator. The only difference is there's just some component values which are slightly different, because it does a very similar thing in that I want an intermittent pulse of kind of quite a short duration, because I don't want the high voltage relay to be energized for long periods of time. It wants to be switched on and off quickly, so that what we actually want to do is we want to just fire the relay to discharge the main high voltage capacitors into the device under test. So that's you know, that's the function of this thing. So what I was actually doing here is I've actually got one of the wires on the 555 timer, which is DC, which is the discharge path. So what I'd actually done is I've actually connected a switch in line with this discharge path. So what I can actually do is when I actually open the switch, it stops the discharge path from working. It stops this capacitor here, which is used as the timing component. It stops this capacitor being discharged. But the problem that I've got is that once you actually open up that discharge path, is the output here just goes low. And I think really it's kind of a fundamental problem, I'm afraid, that I really didn't properly understand how a 555 timer works. Well, in my defence, I've never actually used one before, you know, 30 years been into electronics, and in all that time a 555 timer has never crossed my path. As soon as I found that my circuit wasn't working, I went and had a look at the way that this thing works, and I think I understand what the problem is. Inside of here there's actually a flip-flop, and it kind of toggles between well, like flip-flops do, it toggles between one state and another. So I think what's actually happening is it's actually stopping. When I actually disconnect this discharge path here, it's actually sticking in one state. And the other thing which I really can't seem to quite get my head round is I did actually breadboard this circuit, and I tried it and it works. Now I've actually built it onto a PCB, it doesn't work. I think if I managed to get it working previously, that was definitely more luck than judgment. So I've got to say I'm actually quite embarrassed about this. I've kind of shown my lack of knowledge here with 555 timers, just to actually get this circuit working and you know, get this finished. I'm probably going to do some bodging. I'm going to put a switch up here somewhere, and I'm just basically going to bias these transistors fully on with a push switch. So I'm going to tweak the circuit on the back of the board to try to get that to work as I intended it. But yeah, I'm a bit embarrassed there. But what I think I'll do next, I think I'll just finish off this circuit, because we've only got the sound driver to add to this now, which is just a piezo sounder and a little transistor switch. So let's go ahead and add them components, and then when we've got the circuit working and this thing will be bleeping away, hopefully, we'll go away and I'll just put some bodge wires on the back of the circuit, and well, it wouldn't be a prototype, would it, if we didn't have some Billy bodge wires on there. So I will do that. So here's the piezo sounder that we're going to install. Now there's a couple of different types of piezo sounders that you can buy. Some of them are literally just a piezo element, and what you do is you need a driver circuit which will provide like a high frequency square wave to it. Well, these that I'm using, these have actually got a driver circuit built into them, and it just makes them a little bit easier to use. And when you're buying these sounders in low quantities, it really doesn't seem to make a lot of difference whether you buy the passive version or the active one. The cost is about the same. So I generally buy these active ones because they're just a little bit easier to drive. unless you've got another 555 timer, or maybe you can build a transistor oscillator, you know, they're a little bit of a pain. If you've got a microprocessor circuit, you can usually just use one of the digital output pins to provide like a 1 kHz square wave or something, and you know, it's fairly easy to drive them like that. But we don't have a micro one here, so we'd have to build either a transistor oscillator or maybe use another 555 timer to produce the actual driver waveform. It's got a little positive on it, so I'm just making sure I get it on the right way around. The supply voltage for our ESD gun, it's actually going to be around probably around 13.5 volts, 12 to around 13.5 volts. The actual piezo sounder that I'm going to use, it actually operates from I think it's something like a 3.5 to 4.5 volt supply. It's actually quite a low supply it's designed to operate from. So what I've had to do is within my driver circuit here, I'm using just a Zener regulator, because I haven't got actually a low voltage regulator on this circuit board. It's actually using most of these op-amps, sorry, these 555 timers will operate quite happily at 13 volts. So I didn't put any form of regulator on here, and because of that I'm going to have to just drop the voltage down to a suitable level to operate our piezo sounder. So as I say, what I've just built onto the circuit here is just a simple Zener regulator to do that. When it comes to making your own circuit boards, you can actually buy these things now so cheaply from China. It doesn't really make a lot of sense to actually do your own circuits at home. It's still quite good fun to do it, and I've actually quite enjoyed doing this. So even though in one way it doesn't make a lot of sense to make your own boards anymore when you can buy them so cheaply, I've enjoyed doing it, and I think I probably will make some of my own boards in the future, especially if it's a one-off. One of the problems that I always find is when you're doing projects, it's very easy to get kind of bored with the projects. I don't really like big projects. I get distracted, I get bored too easily. So if you've got to send your your design off and then wait for 2 or 3 weeks to, you send it for China, and then you probably get 5 boards of this for probably less than 20 quid or around that. The shipping can be expensive, but it always takes maybe 2-3 weeks before you get your board back, and that waiting time can actually just be a killer for enthusiasm. I think if I was making this circuit board again, I would change some of the design rules in my electronics CAD software, and I would have actually pushed the gap between the tracks and the ground plane. I would have opened them out just a little bit more. Well, we seem to be about finished, so all I've got to do is figure some way of bodging this switch in to get the continuous mode, and then we will be done. So let's turn this off and I will implement some bodgery. So I'm afraid we're going to have to get a little bit medieval on this thing. Out comes a Stanley knife and I am going to be cutting some tracks. So the first thing that I'm doing here is I'm actually removing the switch. I'm removing it out of circuit. Now I still want to use the connector. I want to reuse that so that all the bodgery and nastiness, I'm going to try to hide that on the underside of the board as though it never happened and you guys won't ever know it happened. So I've just implemented a quick bodge there. So what I've done is I've taken a bodge wire between the top of these 2 diodes here, D1 and D2, and I've actually strapped out and gone directly into the input of our 555 timer on pin 7. So I've actually freed up this header now to do some more shenanigans with. Like I bought one, that's factory that is.